Welcome everyone, I'm TH, and as a flight instructor, it is absolutely my privilege to guide you through this explainer today. Now you're here because you aren't just looking to pass a basic written test. You're aspiring professionals, dedicated to studying and training to become commercial pilots, and let me tell you, the material we're covering today, it's about mastering the incredibly powerful atmospheric engine that you will soon be operating within. So let's dive right into this deep analysis of aviation weather theory.
Think about it this way. When you finally take that left seat, you're not just flying a piece of machinery. You are commanding a vast, invisible, and deeply dynamic ocean of air. And this atmosphere, it's in a constant, restless struggle to establish an equilibrium that, frankly, it can never actually reach. That's why meteorological theory isn't just some rote memorization exercise. No way! It's the foundational, literally life-or-death knowledge required to protect your future crew, your passengers, and your airframe. The physics of the atmosphere dictate everything from your fuel calculations right down to your very survival. So let's look at exactly how we're going to break this all down.
Here's the syllabus for our explainer. First, pressure systems and wind dynamics. Number 2, stability in the adiabatic process. Third, navigating dangerous temperature inversions. Then we'll cover moisture, humidity, and cloud bases. And finally, number 5, the aerodynamic hazards of frost.
All right, jumping right into section 1, pressure systems and wind dynamics. These are the prime movers of weather.
Okay, so what kicks all of this off? Every single weather phenomenon you'll ever encounter begins with one catalyst, the unequal heating of the Earth's surface. This unequal heating changes the air density, which, in turn, creates massive differences in atmospheric pressure. Now, as commanding pilots, you absolutely must know how to read and interpret isobars during your pre-flight prep. These are the lines that connect areas of equal pressure. Essentially, they reveal the pressure gradient, or how much the pressure changes over a specific distance. When you look at your weather charts and see those isobars packed tightly together, you need to immediately anticipate a steep wind gradient and strong, potentially severe winds along your route.
Now, if we visualize the three-dimensional structures of high and low pressure systems, there's a fascinating dynamic at play. High up at altitude, air desperately wants to blow directly from high pressure straight into low pressure. But the Earth's rotation introduces something called the Coriolis force, which actually deflects this air to the right. So aloft, the air ends up flowing parallel to the isobars. But what happens when we bring our aircraft closer to the ground? Well, down near the surface, the physical friction between the air and the Earth's terrain actually reduces that Coriolis force. Because of that friction, surface air flows across the isobars. It spirals outward and clockwise from the center of a high and inward and counterclockwise into the center of a low.
Let's sharply contrast these two environments, because they mean very different things for you in the cockpit. A high-pressure center is basically a massive area of cold, sinking air surrounded by lower pressure. As that heavy air descends, it compresses, it dries out, and it creates really stable, clear, and generally favorable flying conditions. A low-pressure center, on the other hand, is an area of warm, rising air surrounded by higher pressure. And this rising air, it is highly unstable. It leads to increased cloud development, precipitation, and just generally bad weather conditions. As a commercial pilot, navigating your aircraft toward a low means you better be mentally preparing your cockpit for a heavy, demanding workload.
Moving right along to section 2, stability and the adiabatic process. This is what governs vertical motion in the atmosphere.
So, atmospheric stability is, at its core, simply the atmosphere's resistance to vertical motion. Stable air makes vertical movement really difficult, while unstable air basically encourages it. To truly grasp this, we have to talk about the adiabatic process. As air rises into areas of lower pressure, it naturally expands into a larger volume, causing its molecules to spread out and cool. We call this adiabatic or expansion cooling. Conversely, when air descends, it moves into higher pressure, condenses into a smaller volume, and that compression heating causes its temperature to increase. Now, here's a baseline constant every single commercial pilot must internalize: the standard temperature lapse rate. That rate is 2 degrees Celsius, or 3.5 degrees Fahrenheit, of cooling for every 1,000 feet of altitude gain. Burn that number into your memory.
Now, this next part is a bit counterintuitive, but water vapor is actually lighter than dry air. To put that into perspective, did you know a single average cumulus cloud weighs over 1 million pounds? 1 million pounds! Yet it just floats effortlessly above us. How is that even possible? Well, it's because that massive amount of water vapor is literally less dense than the dry air surrounding it. And this is a totally critical mathematical reality governing stability. Adding moisture decreases air density, which causes that air to rise. Dry air, on the other hand, cools at a much faster rate. The dry adiabatic lapse rate is about 3 degrees Celsius per 1,000 feet. Because it cools so quickly, it just doesn't rise as high before its temperature matches the surrounding air, so it's highly stable. But moist air, it cools at a significantly slower rate, anywhere from 1.1 to 2.8 degrees Celsius per 1,000 feet. Because it hangs onto its heat longer, it just keeps rising higher and higher before cooling to ambient temperature, and that right there creates dangerous atmospheric instability.
Let's translate these physics directly into your daily operational realities. Cool, dry air practically guarantees very stable conditions. It gives us that clear, smooth, favorable weather we all absolutely love to fly in. But moist, warm air? Listen to me, that is the ultimate recipe for extreme instability. It's exactly what breeds towering clouds, low visibility, and violent thunderstorms. You absolutely must respect the destructive potential of moist, warm air masses.
Okay, Section 3. Navigating dangerous temperature inversions. Let's look at what happens when the normal rules flip entirely and temperatures actually rise with altitude.
An inversion is a really highly deceptive anomaly. Picture a shallow layer of smooth, stable air close to the ground. There's little to no wind, but as you climb, the temperature actually increases. That specific point where the temperature starts increasing aloft acts exactly like a giant lid. And this lid traps fog, haze, smoke, and pollution tightly beneath it. If the relative humidity is high on a day like this, you're going to encounter drastically degraded visibility near the surface. It makes your approaches and departures incredibly hazardous, right up until you can punch through that inversion layer.
In the field, we categorize these primarily into two types. First, think about what happens on a clear, cool night with calm winds. The ground cools off rapidly, which then cools the air immediately touching it, making the surface air cooler than the air right above it. This creates what we call a surface or ground inversion. Frontal inversions, though, are much more dynamic. They happen when a weather front violently pushes warm air to spread over a layer of cooler air, or physically forces cooler air tightly under a layer of warmer air. Both of these scenarios demand your absolute, acute situational awareness, particularly regarding visibility and the massive potential for wind shear.
Moving on to Section 4, moisture, humidity, and cloud bases. It is time to calculate our visible threats.
So humidity is simply the measure of moisture in the air. Relative humidity is a bit different. It compares the actual amount of moisture present to the absolute total amount the air could possibly hold at that specific temperature. And this whole system is driven entirely by changes of state, meaning liquid, solid, and gas, and the transfer of latent heat. Let's track this complex flow of energy. When water transitions from a solid to a liquid to a gas, so melting, then evaporating, or directly sublimating, it actually absorbs latent heat from the environment. Conversely, moving from a gas to a liquid to a solid, condensation, freezing, or direct deposition, releases massive amounts of latent heat back into the atmosphere. And let me be clear, this violent release of heat is the literal engine that powers severe storm development. So the crucial takeaway here is understanding the dew point. The dew point is that exact specific temperature at which the air reaches 100% relative humidity. It hits a saturation point where it simply cannot hold even one more drop of water vapor. When the ambient temperature and the dew point converge and become equal, boom, saturation is achieved. At that exact altitude, or down on the surface, the water is forced to change state, instantly triggering the formation of fog, low clouds, or precipitation. So how exactly does the atmosphere pull the trigger on this saturation? Well, as a commercial aviator, you need to actively anticipate 4 specific atmospheric triggers. First, imagine warm air moving over a cold surface, which cools the air from below. Second, consider the chaos when cold air and warm air are violently mixed together. Third, think of air cooling at night just from coming into contact with the much cooler ground. And finally, fourth, air being physically lifted upward into lower temperatures, causing that expansion cooling we talked about until saturation is reached. I promise you, if any of these 4 conditions exist on your route, you are guaranteed to encounter visible moisture.
Let's move to how this builds into your practical flight planning. You can actually precisely calculate the altitude of a cloud base above ground level. Here is the exact math you must master, and honestly, it's simpler than it looks. Unsaturated air cools at a very predictable 3 degrees Celsius or 5.4 degrees Fahrenheit per 1,000 feet. Meanwhile, the dew point temperature drops at a slower rate of 0.5 degrees Celsius or 1 degree Fahrenheit per 1,000 feet. This means the ambient temperature and the dew point converge at a rate of exactly 2.5 degrees Celsius or 4.4 degrees Fahrenheit for every 1,000 feet of altitude you climb. So by calculating the spread between your surface temperature and your dew point and dividing it by this convergence rate, we can pinpoint exactly where those clouds are going to form. It's a fantastic tool to have in your kit.
And finally, Section 5, the aerodynamic hazards of frost. This right here is the silent killer on the airframe.
we're bringing our atmospheric physics directly out of the sky and right down onto the tarmac. Both dew and frost happen on calm nights when the ground temperature causes the surrounding air to drop below its dew point. However, dew forms when the ambient temperatures are relatively warm. The moisture in the air condenses neatly into a liquid on the surface. Frost, though, is critically different. Frost forms on cold nights when the temperature of the ground drops below the freezing level and below the dew point. When that happens, the moisture in the air changes state directly from a gas to a solid. We call this thermodynamic process deposition, and it rapidly coats your entire aircraft in tiny ice crystals.
I cannot stress this enough. Do not ever underestimate frost. When frost covers the surface of an airplane, it violently disturbs the incredibly smooth, critical airflow over the wing. This seemingly harmless thin layer significantly destroys your lift and drastically degrades your climb performance. It is a known, utterly unforgiving hazard. Both legally and practically, you as the pilot must ensure the absolute removal of all frost before flight, period. Attempting to take off with frost on your wings isn't just physically dangerous, it is a profound failure of command.
Well, that brings us to the end of our explainer. Listen, the atmosphere doesn't care about your schedule, it doesn't care about your VIP passengers, and it certainly doesn't care about your ego. It operates strictly on the cold, hard physical laws of pressure, stability, and moisture that we've just dissected together. So I'm going to leave you with this final thought as you continue your training. Will you respect the unforgiving laws of atmospheric physics before you take the left seat? Mastering this theory is not just an academic exercise to pass a test, it is the ultimate prerequisite for command. Study hard, fly safe, and I will see you in the sky.